In this video, we're going to look at CC4, which is the periodic table, and it's a topic that comes up on paper 1 and on paper 2. The periodic table was created by a guy called Mendeleev to organise all of the elements that were known at that time. On the modern periodic table, the one we've got today, there are two numbers next to every element. The smaller number is called the proton number, and it tells you how many protons there are, and the larger number is called the mass number. It tells you how heavy the atom is, and it is a sum of the protons and the neutrons in the element. When Mendeleev was creating his periodic table, protons hadn't been discovered, so all he had to go on was the mass number. He used this mass number to arrange the elements, and he arranged them according to increasing atomic mass. Okay, that word increasing is important. It tells you that he started with the element with the smallest mass, and that they increased as he went through his periodic table. I have a picture here of what his periodic table looks like. So obviously there are a lot less elements than what we've got today because most of them hadn't been discovered yet. But you can see that there's only one number next to each element. This number here is the mass number. And if you're going from left to right, you can see that that number is increasing as you move across the periodic table. However, if you come all the way down here, you'll see that he has an element with 122 going to 128 and then back to 127. So with tellurium and iodine, he didn't arrange them according to increasing atomic mass, instead choosing to put iodine after tellurium. The reason he did this was because he also wanted to arrange elements in groups based on their chemical properties. By chemical properties, I mean how they react in a chemical reaction. So you can see over here that he's got lithium, sodium, and potassium all in the same group because they're all metals and they all react in the same way. Over here, he's got fluorine, chlorine, bromine, and iodine, and he wanted them all in the same group because they all react in the same way. Because of this, he chose to put iodine after tellurium, even though its mass was smaller, because he wanted iodine in the same group as bromine, chlorine, and fluorine because they had similar chemical properties, because they reacted in the same way. You'll also notice that there are a few gaps on his periodic table. They're for elements that he believed hadn't been discovered yet. So if we look over here, he didn't want to put titanium straight after calcium because he didn't want titanium in the same group as boron and aluminium. He predicted that there was another element that hadn't been discovered that had the same properties as boron and aluminium. And he was right. Okay, gallium was discovered later, and that had similar properties to boron and to aluminium. So when you're talking about Mendeleev and how he arranged his periodic table, you're going to say he organized elements according to increasing atomic mass, and he put them in groups based on chemical properties. You could also add that he left gaps for elements that had not been discovered. I've got some worked examples here to show you typical questions that come up on Mendeleev. The main one being just how he organized his periodic table in order of increasing atomic mass. And I've highlighted that word increasing because it is required for the mark. You can also say elements with similar properties were put in the same group. What we also discussed, why iodine was placed after tellurium, because he wanted iodine in the same group as the other halogens because they all have similar chemical properties. He left gaps for elements that had not been discovered, and he was then able to predict those properties based on the elements of the based on the properties of the elements around. So they are four kind of typical questions that you can be asked on Mendeleev. If we move from Mendeleev's periodic table to the modern periodic table, you can see first off that there's a lot more elements now, so way more elements have been discovered, and you can also see that there are two numbers next to each element. You still have the mass, which Mendeleev had, but you now also have a second number, which is the number of protons. So the atomic number, or the proton number, is the smaller of the two numbers. It tells you how many protons are present. Instead of arranging the elements according to increasing mass, the elements are now arranged according to increasing atomic number. And by arranging according to increasing atomic number, the problem Mendeleev had with iodine being in the wrong group is solved. Okay, so if we look at increasing atomic mass, iodine should become before tellurium, and that would take it out of the group with bromine, chlorine, and fluorine. But if you look according to increased atomic number, iodine comes after tellurium, which puts it in the same group as the other halogens, and in the same group as the elements that have the same properties. The other thing I want to point out with the modern periodic table is the presence of the noble gases. None of these elements are present in Mendeleev's table, mainly because they're all unreactive, because they've already got their full outer shell, and because they're unreactive, they were difficult to discover. As well as being arranged according to increasing atomic number, again, in the modern periodic table, elements are based in groups according to their chemical properties. And their chemical properties are directly related to their electron configuration. So electron configuration just relates to how electrons are arranged. We already know that electrons are found in shells surrounding the nucleus, and you need to know how many electrons each shell can hold. So the first shell, the shell closest to the nucleus, can hold 2 electrons. The second shell can hold 8 electrons. The third shell can also hold 8 electrons. We can use this information to draw electron shell diagrams. So if I were to draw one for lithium, the small number next to lithium is 3, which tells me it's got 3 electrons. I would draw 2 electrons in the first shell, the shell closest to the nucleus, and then I would need to move into the second shell to draw that third electron. I do something similar for sodium, which has 11 electrons. Again, I start putting electrons into the first shell. I put in 2. I then must move to the second shell because the first shell is full, and I can put in 8, which means I've drawn 10 electrons in total. I now need to move to the third shell, and I draw 1 electron in the third shell to give me 11 electrons in total. This is what you would do if you were asked to draw electron shell diagrams or to draw a diagram to represent electron configuration, but you can also just be asked to write electron configuration. So if I look at potassium, which has an atomic number of 19, so it has 19 electrons, if I was asked to just write the electron configuration, I would just write down how many electrons are in each shell. So in the first shell there would be 2 electrons, then I would move into the second shell and put 8, which gives me 10 in total. I then need to move into the third shell where I could put another 8, which gives me 18 electrons in total. And then that last electron will go into the fourth shell. So to write the electron configuration, it's just 2, 8, 8, 1. Lithium, sodium, and potassium are all in group 1, and they're in group 1 because they've got the same chemical properties. The reason they have the same chemical properties is because they all have something in common in terms of their electron configuration. If you look at all 3 of them, they all have 1 electron in their outer shell. When you're doing chemical reactions, it's the electrons that you're concerned with. Okay? You're not looking at the protons or the neutrons in the nucleus. It's all about electrons for chemical reactions. And it's not the inner shell electrons that are involved, it's always the outer shell electrons. The fact that lithium, sodium, and potassium have the same number of electrons in their outer shell means they're going to react in the same way. It doesn't matter that potassium has way more electrons than lithium, you're only looking at the outer shell. The other thing that you can see in terms of electron configuration is as I move from lithium to sodium to potassium, I'm adding an extra shell each time. Lithium only needs 2 shells, sodium needs 3, potassium needs 4. And if I go back and look at my periodic table, and I look at the period number, so group number is the column going down. The period would be the row going across. So hydrogen and helium are in period 1. Lithium, beryllium, and all these elements over here are in period 2. Sodium is the start of period 3, and then potassium will be the start of period 4. And that period number tells you how many electron shells you're going to need in order to fill in all those electrons. So for hydrogen and helium, you only need to draw 1 shell because both of their electrons will fit in their first shell. If you move down to period 2, you'll need to draw 2 electron shells. Down to period 3, you'll draw 3 electron shells. Down to period 4, you'll need to draw 4 electron shells. So using your periodic table, if you were asked how many occupied electron shells does carbon have, you don't even need to draw out the diagram. Carbon is in period 1, 2, therefore it's got 2 occupied electron shells. How many occupied electron shells does calcium have? Calcium is in period 1, 2, 3, 4, so it's got 4 occupied electron shells. Similarly, with the number of electrons in the outer shell, you can just use the group number. We've already seen that all group 1 elements have 1 electron in their outer shell. If you were to look at all of the group 4 elements, they would all have 4 electrons in their outer shell. The group 7 elements would all have 7 electrons in their outer shell. The group 0 elements all have full outer shells. So helium has got 2 electrons in the first shell, which is a full first shell. Neon, argon, and krypton all have 8 electrons in their outer shell, which is a full outer shell. So they've all got full outer shells. It's a really common exam question where they'll ask you to describe how the elements are arranged according to electron configuration. So again, electron configuration just means how the elements are how the electrons are arranged. And what you would need to say is that elements in the same group have the same number of electrons in their outer shell, but elements in the same period have the same number of electron shells. So that's how you would answer that there. You're not going to get any marks for talking about increasing atomic number because you're specifically asked about electron configuration. The other worked examples I've done here, simpler, okay? How many does magnesium have in its outer shell? It's in group 2, so 2 in its outer shell. How many nitrogens in group 5? So 5 in its outer shells. And then in terms of electron configuration, what do lithium and nitrogen have in common? If we look at the periodic table, lithium and nitrogen are both in the same period. Therefore, they both have the same number of electron shells. And because it's period 2, it's going to be 2 electron shells. The most common mistake with this is neglecting period 1. Okay, so hydrogen and helium are in period 1, and what often happens when you're counting your periods is you start here with lithium and you go 1, 2, 3. Okay, please make sure that you start with hydrogen. Hydrogen is 1, lithium is period 2, sodium's in period 3. Okay, if in doubt, draw yourself a quick electron shell diagram. You'll see you need 2 electron shells for lithium. That tells you it's in period 2. So I've got some questions here. At this point, you should press pause, have a go at answering these questions for yourself, and then press play when you're ready to see the answers. Okay, so if we go through the answers, who created the periodic table? Mendeleev. How are they arranged? According to increasing atomic mass and put in groups based on chemical properties. He left gaps for elements that had not been discovered. In the modern periodic table, they're arranged according to increasing atomic number. They're also in groups based on their chemical properties. These should all be fine. I'm going to come down to these ones, okay? An element in period 1, hydrogen or helium, okay? That's period 1. An element in period 2, you can say lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, or neon. Group 2, period 2 is going to be beryllium. Make sure you're counting your periods correctly. Group 5, period 2 is nitrogen. Group 7, period 3 is chlorine. Writing electron configuration, you don't need to draw out the shells, you just need to write how many electrons you would put in each shell. Potassium has got 19 electrons. Make sure you're using the right number from the periodic table when you're doing this. You're always taking the smaller number for electrons. So 2881. Sulfur has got 16 electrons, so 286. Carbon has got 6, so 24. And lithium has got 3, so 21. And again, if you look at the electron configuration, I can know straight away that potassium must be in period 4 because there are 4 shells, and it must be in group 1 because there's 1 in the outer shell. Sulfur must be in period 3 and it must be in group 6. Carbon must be in period 2 and in group 4. Lithium must be in period 2 and in group 1. In section B, I've put in that question about electron configuration. It's 4 marks. The answer is above. Do make sure that you can answer that one. It's for 4 marks. Elements in the same group, same number of electrons in their outer shell, same period, same number of electron shells. That is quite a common question on the periodic table, and it's worth 4 marks. So just make sure that you know how to answer it.